Something arrived from the empty space between stars. When we first saw it, this third visitor from beyond looked like a regular comet. Then it began doing things that didn't make sense. Its tail pointed at the sun instead of away from it. It gave off nickel, but had no iron with it. It contained chemicals that shouldn't be there. Every time we looked closer, one fact became clearer. This thing didn't match our expectations. It didn't fit our models, our categories, or even what we thought was possible in nature. The odds of all these strange things happening together are 1 in 10 to the 16th power. Each unusual feature has about a 1% chance or less, and there are 8 of them. It's extremely unlikely we'd see all of these weird things at once. Atlas is more than just another visitor from outside our solar system. It's a break in everything we know. It's forcing scientists to rebuild what they thought was true. When you see something impossible, you can't keep pretending the old rules still work. This is the story of how Atlas changed science forever. In July 2025, telescopes in the southern half of Earth spotted something odd moving in the sky. It was drifting slowly from where the center of our galaxy sits. It moved too fast to dismiss, but was bright enough that we couldn't ignore it. What they found was real, and it was heading right through our solar system. At first, it looked normal, a distant dot, with a faint hazy cloud around it. The type of thing astronomers might write down and move on from. But its path was all wrong. The orbit curved like a hyperbola and went backward compared to everything else. It wasn't circling the sun like planets do. Instead, it was cutting through the flat plane where planets orbit at a gentle angle, just 5 degrees off from where Earth travels. It almost seemed like it knew which way we were going. They named it Atlas. It was the third confirmed object to visit us from another star system. Before it came Oumuamua in 2017, which sped up in ways no natural object should. Then came Borisov in 2019, a comet that looked more normal but had strange chemistry. Both raised questions that we couldn't answer before they left. But Atlas was different. It was bigger, brighter, slower, and most importantly, easier to study. For the first time, we had enough time to observe it, measure it, and track it. From the start, things seemed off. The hazy cloud around it was brighter than it should be for something its size. Its tail wasn't streaming behind it like normal. Instead, it pointed forward toward the sun. The dust particles it released didn't act like regular dust. They pushed back against sunlight. They moved in ways that didn't match how comet material should behave. Some scientists thought maybe the grains were bigger than usual. Others suggested the surface might have unusual textures. None of these explanations felt right. Then came the orbit analysis. Atlas wasn't just passing by. It was threading its way through the solar system. First it went near Venus, then Mars, then Jupiter. This sequence of planets was so exact that scientists had to recalculate the statistics. Avi Loeb, an astrophysicist at Harvard, figured the chances of such a path happening by accident were about 1 in 20,000. This doesn't prove someone planned it, but it definitely needs explaining. For many scientists, Atlas was just an old piece of ice, a frozen chunk from a dying star system that got thrown into space long before Earth even existed. But for others, it became something more, a puzzle that seemed too deliberate to be random. A visitor that brought questions written into its very structure. The more scientists studied it, the stranger it got. Atlas wasn't acting like a comet. It was acting like something that didn't fit any category. And that's when the real mystery started. It began with an unusual glow patterns of light that didn't belong. When scientists aimed the James Webb Space Telescope and Hubble at Atlas, They expected to find the usual stuff: water vapor, carbon-based compounds, traces of rock material, maybe some iron, possibly some organic dust. Instead, they found something much stranger. The object was releasing nickel, not tiny traces or hints, but actual measurable streams, about 4 grams every second. That alone would have surprised people. But what happened next broke everything we knew about comet chemistry. There was no iron, not a little bit, none at all. In every comet we've ever seen, iron and nickel come together. They were born together inside ancient stars and stuck together in the rocky debris of planets. They boil off together when heated up. But Atlas had separated them. Nickel was escaping freely, while iron stayed completely quiet. And this wasn't just simple nickel atoms. It was something more complex. Among what it was releasing, scientists found nickel tetracarbonyl, a compound we know on Earth almost only from metal factories and aerospace engineering. This molecule is so unstable, it rarely forms in natural settings and never, until now, in deep space. This was more than just weird. It broke the rules. Some scientists suggested Atlas might have formed in an unusual part of its home star system, where iron froze into solid minerals while nickel stayed as a gas. Others thought maybe centuries of radiation in space had changed its outer layers in specific ways. But none of these ideas could fully explain why an industrial compound was floating around in space. And none could explain what the object was doing with carbon dioxide, because along with the metal signature, Atlas was venting gas CO2 in amounts that were even greater than its water vapor release. The numbers were striking: 8 parts CO2 for every 1 part H2O. This type of chemical makeup doesn't match anything in our list of known comets. It doesn't line up with any solar system chemistry we've recorded. It points to a birthplace far beyond what we understand, somewhere cold, violent, and completely alien. Then came the light readings. Measurements of dust scattering showed patterns we'd never seen before: negative polarization, something usually linked to surface textures, unlike anything we've come across. It was as if the dust grains themselves had different shapes, or were built in a different way. Put together, these details started forming a picture, not of a comet, but of something else. An object shaped by rules we don't know yet. Chemistry that suggests either a natural process we never imagined, or something we weren't expecting to find. Atlas didn't just break our models. It shook our confidence in knowing where nature stops and the unknown begins. Science was never supposed to be easy or comfortable. It starts with wonder, but moves forward through finding contradictions. We build models not to lock in the truth forever, but to test it, push them until they fall apart. When they break, we have a choice: ignore the crack or dig deeper into it. With Atlas, the crack is real now, not just theoretical. What started as a comet-like object with a weird path quickly turned into a challenge to everything we've believed about how small space objects work, how chemistry happens in space, and what matter from other star systems should look like when it enters our neighborhood. The first problems showed up in the dust and gas it released. Nickel without iron, lots of carbon dioxide, organic compounds that seemed better preserved than anything we've seen near the sun. But these were just individual pieces of data, and science is good at handling data. It adjusts, reshapes, and grows. New theories came out. Some suggested that in the alien region where Atlas was born, the chemistry of leftover planetary material worked differently, one where volatile nickel compounds formed and iron got trapped deep inside. Others pointed to selective damage from radiation over billions of years in deep space. This might explain the chemical imbalance, if not the presence of nickel tetracarbonyl, that industrial molecule from Earth. Looked at one by one, the weird things could each be explained. But together, they started to resist being fit into our understanding. Then there was the orbit backward, shallow, a path that didn't dive from above or below, but slid almost along the same flat plane as our solar system, 5 degrees off the ecliptic. That alone is rare. But the route it took passing Mars, Venus, then Jupiter was even more troubling. Avi Loeb, the Harvard astrophysicist known for challenging ideas, calculated that such a flight path had about a 1 in 20,000 chance of happening randomly. The sequence wasn't just interesting, it seemed precise. Now, precision doesn't prove someone meant it to happen, but it raises the stakes. It invites the question every careful scientist fears. What if this isn't random? What if there's more to it? Most scientists remain cautious, unwilling to jump to ideas about artificial origins. And for good reason. The universe is huge. What seems strange is often just unfamiliar, waiting to be understood. But something about Atlas has shifted how people talk about it. The pushback against alternative ideas isn't as strong as it was with Oumuamua. There's more humility now, an understanding that objects from other star systems might not follow our rules, that our rules, in fact, might be way too limited. We've only confirmed 3 visitors from beyond our system: Oumuamua in 2017, Borisov in 2019, and now Atlas. Each one stranger than the one before. Each one bringing questions our models weren't ready for. We can't assume anymore that all objects from other star systems are simply frozen leftovers. They're not consistent. They're not predictable. And increasingly, they can't be explained easily. This realization is changing more than just our theories. It's changing how we view the cosmos. Where we once looked outward with the comfort of assuming other star systems would be like ours, we now face the possibility that we're the unusual ones, that other parts of the galaxy might produce matter, movement, and behavior completely different from what we understand. This kind of fundamental shift is rare, but it has happened before. In the past, we learned to accept that Earth isn't the center of everything. We learned that time bends, that space stretches, that particles can vanish and reappear for no clear reason. Each time, science didn't fall apart, it adapted and grew. Now, Atlas might be demanding that growth again. Whether it's natural or not, alien or ordinary, Atlas isn't the odd one out. It's showing us that our models were always incomplete, and that the universe is still writing chapters we haven't learned how to read yet. And that's the most important discovery. Our understanding has limits. The most annoying thing about discoveries like Atlas is that they don't wait around for us. They keep moving, unbothered by our questions, unaffected by our curiosity. And now, as it gets closer to the Sun, Atlas is disappearing from view, just when things were getting really interesting. As it reaches its closest point to the Sun, we face both opportunity and loss. As the heat grows stronger, deeper layers of frozen material might wake up. Jets could shoot out. The surface might crack open, showing secrets locked away since before our Sun even formed. But for an important stretch of time, we'll see none of it. The Sun's glare will blind our best telescopes. Hubble can't follow it. Webb has to look away. The most important phase of how it behaves might happen in silence, unwatched, unrecorded, unsolved. There are some options. The Juno and Psyche spacecraft, already traveling through the inner solar system, will pass close enough to observe. But they weren't designed for this. Their instruments aren't set up for comets, and their missions aren't meant to change direction. Still, Some scientists are pushing to reprogram them small changes in their paths that might capture something, anything. And then there's Juno, circling Jupiter with low fuel and a damaged main engine. Juno has been suggested as a long-shot possibility for getting closer. The idea is bold, risky, maybe impossible, but it shows how seriously scientists are starting to take this object. Atlas might never come back, and letting it vanish without trying to reach it halfway feels almost careless. This isn't just a rock from another star system. It's a question we might not get to ask again. If we miss this opportunity, if no pictures are taken, no close approach is made, we'll be stuck with only the information we've already gathered enough to hint at answers, not enough to actually explain them. And that's what makes this moment so hard. Not the mystery itself, but the fact that it might go unanswered. Long after it's gone, drifting alone in the darkness, the arguments will go on. Scientists will debate its nature, its chemistry, its path. But the object itself will have left. And with it goes the best opportunity we've ever had to learn what it truly was. Because even in science, some chances are lost forever.